Hi, Year 11. Sequence of videos now to just go over a 2019 past paper, paper 1, and you'll see that it's higher tier. So I'm going to go through question by question and do a mini video for each question. So your first one here is, it talks about the work done to bring a car to a rest is given by this equation. Work done equals the braking force times distance. This is fat, wobbly dinosaurs, as we've learnt it in the past. And it says, which of these graphs is correct for the car if a constant braking force is applied? Well, a way to think about it mathematically is we can see that we've got three factors and they're directly related. So anytime we have a formula with three things like this, we know we've got direct proportionality. And a way to think about this is I could put some numbers in to say, well, let's fix F as 1. And I can see that F equals W over D. So an example now is, well, I know that, let's say the work is 2, the distance must be 2 to give me 1. Well, if I'm going to keep 1 constant, if this number went to 3, this number's going to go to 3. So what we can see is, well, 1, 1, 2, 2, 3, 3. So we can see that there's a pattern. For me to try to keep this direct proportionality, it's, well, as one factor increases, the other increases by the same amount. So we know it's this one here. We know it's A. So I'm going to put a little X there. And I can see, well, here the factors aren't related. So for C, the one factor doesn't affect the other, just stays constant. This one is, it's as one thing's changing, the other one's changing at an increasing rate, and this one is one's changing at a decreasing rate. So we can now see the only one it can be is A. And a way to think about it is anytime I have an equation with three factors related, it is direct proportionality, and we know that's a straight line there. And we could fit an equation to it if we wanted. So the next one now is, it says we've got a car, it brakes and it has kinetic energy. So you can imagine I've got a car, it applies the brakes, and let's say it's moving at 2 meters per second. When it applies the brakes, it's stopped, 0 meters per second. So the question is, where's that kinetic energy gone? So we know, well, Ke equals half mv squared. So whatever, and we could use that to calculate if we wanted, but that's not what the question's saying. It's saying, well, where has this kinetic energy gone? And we know through the conservation of energy, energy can't be created or destroyed. So it's going to be transferred to another energy source. And earlier on, I taught you help to suck magnets in terms of the energy stores. Well, clearly what's going to happen is when I press the brakes, the kinetic energy is going to be turned into heat energy in the brakes. And what we can actually say is there's work done to stop the car. Another way to think about this at a very higher tier level is the kinetic energy equals the work done. And I could write it another way, half mv squared equals force times distance, which enables us to work out braking distance, which is nice, but that's pretty advanced for what this question's asking. So it's just saying, well, what's happened to the kinetic energy during braking? And we can just say that it's transferred to thermal energy. Oh, apologies for my writing. In the brakes. And if I wanted to, ... I could then say, and this is dissipated into the air. So in terms of a picture, if I change my colour here, the kinetic energy that this has here is going to be changed into heat energy in the wheels, and that'll then get dissipated into the floor and into the air. So that's your model answer for that one. We've got this one here. Let's have a quick look. Oh yeah, nice question. So change my colour. These weren't done particularly well on your mock, and I think it's just that maybe it's a unit that you've not done in maths in terms of just looking at these and certainly looking at how we calculate units. So the graph in figure 1 shows how the braking distance d, that's this one here, depends on the velocity v, and that's this one here, meters per second. And it says use the equation and data from the graph in figure 1 to calculate a value for c. So I can see here, and I'll do this of one of two ways. Because I've got three factors, if I wanted to, I could change this into a formula triangle. So I've got v squared, c, and d. It's one way of looking at it. Another way is I could rearrange it as you would in maths, so do proper maths on it. So I could say, well, D equals, oh, that's really messy there. Let's make a bit more space over here. So D equals V squared over C. I'll do it a more complicated way in my head. So I want to get C on its own. So D equals, well, if I divide both sides by V squared, I've got D over V squared equals 1 over C, because V squared divided by V squared is 1. I don't want 1 over C. I want C, so I can then rearrange this, and the way to deal with that is I can flip these two over. C equals V squared over D. But you can see, if you can't do that, you can definitely do that. You know, if I've got something divided, that's got to go on top. And then we're ready. We want C. So let's get a nice pretty pink. I want to calculate U. Cover it up. C equals V squared over D. So I can do that first part. Let's change my colour. C equals V squared over D. Next part, it tells you use the graph, which is a target that I'll work on to support you. I'm going to use the graph. I'm going to pick somewhere. Now, in theory, the value for C should be the same along this, and I'm not going to double check it, but I can see that there's an equation fitting it just based on the smoothness of the line. I'm going to pick this point here because I think it cuts nicely. I haven't got any half squares or weird things to read. So I can see, well, my V is 10. Reading across here, that's 8. So I'm now ready to go through. So this is going to equal 10 squared over 8 equals 100 over 8. And I've got my answer, 12.5. Now for the tricky part. So the tricky part is I've got to give this a unit. Well, we can see, and I'm going to just delete a few things here and change my colour. Let's get that nice pink again. Well, my units are, I've got meters per second and I've got meters. So now I can write that as V squared is meters per second squared. So what I've got there is, if I square that, meters squared per second squared. And then I've got to divide that by meters. Okay, so perfect. And we can see that there. So if I was to write that again, that's meters per second squared over meters, because it tells me I need V squared, so meters per second squared. Now that I've got this, I can see, well, I can take M out of both of those terms, and what am I left with? Meters per second squared. So that bit's quite tricky, but I hope this little video helps you with question 1.